arrival and astonishing size. We continue to closely monitor 3E Atlas, an interstellar object approximately the size of Manhattan that is steadily approaching our solar system. Initially, astronomers believed it was just a comet, a familiar type of icy visitor drifting through space. However, recent images have shown something startling. The object appears to have lost its tail entirely, a feature that is usually a defining characteristic of comets. This unexpected disappearance has led some scientists to speculate that 3E Atlas may not be a comet at all. In fact, some even propose that it could be something far more unusual, possibly an artifact of alien engineering, though this remains highly speculative. The James Webb Space Telescope, JWST, has once again revolutionized our understanding of the cosmos. When its incredibly sensitive instruments first detected 3E Atlas, astronomers initially assumed it would resemble other interstellar wanderers, like Oumuamua or 2I, Borisov. Those previous visitors were small, rocky, or icy bodies, ejected from their parent star systems and traveling silently between the stars. But as JWST's infrared sensors began capturing detailed images and spectral data, the picture of 3E Atlas became far more extraordinary than anyone could have anticipated. The object was not small. It was far larger than expected, so immense that it completely challenged our assumptions about how interstellar objects could survive the violent forces required to eject them from their home planetary systems. Unprecedented size and structure. The first observations of 3E Atlas were made as it entered a region of the solar system visible to both ground-based telescopes and JWST's near-infrared camera, NIR-CAM. Initial optical tracking suggested a dim, slow-moving body, probably just a few kilometers across. But as JWST began its deep infrared imaging campaign, that faint speck transformed into a dazzling, complex tapestry of reflected sunlight and thermal emission. By comparing its infrared brightness to predicted reflectivity, astronomers calculated that 3E Atlas could be hundreds of kilometers wide, far larger than any previously known interstellar visitor. This revelation sent shockwaves through the astrophysical community. Objects of this size are extremely difficult to eject from a planetary system. Smaller comets or asteroids can be flung into interstellar space by gravitational interactions with gas giants or by chaotic early dynamics in young star systems. But something as enormous as 3E Atlas implies a far more extreme origin, possibly involving catastrophic events or interactions in densely populated stellar nurseries. Some scientists suggest that 3E Atlas could be a fragment of a dwarf planet, torn apart by the gravitational forces of a nearby star before being ejected into space. Others hypothesize it may be a disrupted moon or even the core of a protoplanet, expelled before it could grow into a fully formed world. Composition and complexity. Juiced spectroscopy revealed that 3E Atlas is not only large but also remarkably reflective and chemically complex. Its surface contains a combination of ices, silicates, and metallic compounds, alongside traces of organic molecules. While some of these compounds resemble materials found in comets from our solar system, their ratios are very different, suggesting that 3E Atlas formed in a region of space with higher radiation levels or unique chemical abundances. Further observations with JWST's mid-infrared instrument, MIRI, detected ammonia hydrates and carbon-rich compounds, signs that the object had undergone thermal processing at some point in its history, possibly due to internal heating from radioactive decay or tidal stresses. Together, these findings suggest that 3E Atlas may not be a simple comet or asteroid at all. Instead, it could represent a fragment of a geologically differentiated world, a piece of a once active planetary body now drifting alone through interstellar space. The size and complexity of 3E Atlas have profound implications for our understanding of planetary formation and interstellar travel. Its enormous scale challenges traditional models, which suggest that large bodies usually remain gravitationally bound to their parent stars. to expel something hundreds of kilometers wide. Extreme gravitational events, such as interactions in dense stellar clusters or close encounters with binary star systems, would likely be required. This hints at a chaotic and violent origin, perhaps in a young, crowded star system where stellar interactions can sling entire planets or planetary fragments into the void between stars. JWST also revealed a tenuous, patchy coma surrounding 3E Atlas, a faint halo of gas venting from the surface. Unlike typical cometary comas, which are generally uniform, this one appears localized, suggesting jets or vents caused by fractures in the crust or heterogeneous surface composition. These plumes also allowed astronomers to refine its rotation rate, which is surprisingly slow, completing a full rotation over several days. Such a slow rotation, combined with immense mass, indicates a cohesive, monolithic structure rather than a loosely held rubble pile. This structural integrity may have allowed it to survive for millions or even billions of years, enduring cosmic radiation, micrometeoroid impacts, and the emptiness of interstellar space. Organic chemistry and prebiotic potential. Spectral analysis of 3E Atlas also revealed complex organic molecules, including polycyclic aromatic hydrocarbons and nitriles. These compounds are known precursors to amino acids, suggesting that prebiotic chemistry could occur universally wherever the right combination of ice, carbon, and radiation exists. While the extreme environment makes the survival of life unlikely, the presence of these compounds lends weight to the theory of panspermia, which proposes that the building blocks of life could be transported between star systems by interstellar debris. Geological history and surface features. Infrared imaging revealed a remarkable surface. Smooth, reflective regions are interspersed with darker, pitted areas, suggesting a history of resurfacing or impacts. Crystalline ice, visible in certain spectral bands, indicates that parts of 3E Atlas experienced heating and cooling cycles, possibly from past proximity to a star or internal energy sources. Its structure, a dense rocky core covered by thick ice and dust layers, resembles icy moons like Europa or Enceladus, raising the tantalizing possibility that it might have once harbored subsurface water, or even environments suitable for chemical reactions akin to those that preceded life on Earth. JUICE's high-resolution thermal mapping also detected localized hot spots, suggesting residual internal heat or ongoing slow chemical reactions beneath the surface. Even in near absolute zero temperatures, these energy pockets hint at the durability and resilience of planetary fragments, capable of retaining their chemical integrity over millions of years. Cosmic significance. 3E Atlas is not just a scientific curiosity, it is a messenger from another star system. Its preserved layers, chemical diversity, and complex structure offer a tangible record of alien planetary processes, providing insights impossible to obtain from exoplanet observations alone. The object demonstrates that interstellar space is not empty but filled with relics of destroyed or failed planets, objects that could seed young systems with heavy elements and complex molecules. Every interstellar traveler like 3E Atlas becomes a bridge across the galaxy, a messenger of matter, energy, and perhaps even the precursors of life. The discovery has also sparked renewed interest in future missions to interstellar objects. Proposed probes could potentially sample material from similar visitors, enabling laboratory analysis of alien matter without leaving our solar system. 3E Atlas, with its massive size and complex composition, serves as an ideal test case for designing trajectories and sampling technologies for these ambitious endeavors. Final thoughts. Every detail of 3E Atlas, from its chemical composition and geological features to its immense size and resilience, reveals a story of planetary evolution, destruction, and interstellar travel. It is a tangible connection between stars, a reminder that matter, energy, and possibly the building blocks of life circulate throughout the galaxy. Its silent journey across interstellar space challenges our imagination, reshapes our understanding of planetary science, and opens new frontiers for exploration. The James Webb Space Telescope, by capturing its faint light, has essentially photographed history itself. Frozen rock and carbon carrying the chemical and geological fingerprint of a long-lost alien world. 3D Atlas is not merely an object drifting through space. It is a window into the hidden architecture of planetary systems beyond our solar system, a relic of cosmic history, and an inspiration for the next generation of interstellar exploration.